In the very beginning, before stars, before galaxies, before even space as we understand it today, the universe existed in a state that is difficult to fully imagine. There were no distances, no directions, and no familiar forms of matter. Everything that would one day become the observable universe was compressed into an extremely hot and dense state. This moment is known as the Big Bang. It was not an explosion in space, but rather the expansion of space itself. There was no center from which everything moved outward. Instead, every region of space expanded at the same time, creating the foundation for what would eventually become galaxies, stars, and planets. In the first fractions of a second, the universe changed rapidly. The temperature was unimaginably high, far beyond anything that can be recreated even in the most advanced laboratories on Earth. Under these conditions, energy dominated completely. Matter, as we know it, did not yet exist in stable forms. During this early phase, the fundamental forces that govern the universe may have behaved very differently. Some theories suggest that gravity, electromagnetism, and nuclear forces were once unified into a single interaction. As the universe expanded and cooled, these forces began to separate, shaping how matter and energy would interact in the future. The expansion itself happened extremely quickly. In a very short span of time, space grew from an almost incomprehensibly small scale to something much larger. This rapid growth laid the groundwork for everything that followed. As the universe expanded, it began to cool. This cooling allowed the first elementary particles to form. Quarks, electrons, and other fundamental components emerged from the dense energy field. These particles were constantly interacting, colliding, and transforming, but gradually they began to form more stable configurations. Even though these processes happened billions of years ago, scientists today are still trying to understand them. Observations made by organizations like NASA and data collected through advanced instruments provide clues about these earliest moments. Telescopes such as the James Webb Space Telescope allow researchers to look deeper into space than ever before. Because light takes time to travel, observing distant objects means looking back in time. In this way, scientists can study conditions that existed long after the Big Bang, but still close enough to reveal important details about how the universe evolved. What makes these first seconds especially fascinating is how much they determined everything that came later. The distribution of energy, the behavior of forces, and the initial fluctuations all influenced the formation of structure in the universe. Even the smallest variations in density during these early moments would later grow into galaxies and clusters of galaxies. Without these tiny differences, the universe might have remained smooth and uniform without the complexity we observe today. There is also a sense of quiet inevitability in these processes. Despite the extreme conditions, the universe followed consistent physical laws. From chaos emerged order, and from simplicity came the potential for everything. And yet, despite decades of research, many aspects of this earliest phase remain uncertain. Scientists continue to refine their models, test new theories, and search for better data. The first seconds of the universe are not only a beginning, but also one of the deepest mysteries in modern science. As the universe continued to expand, the temperature gradually decreased. This cooling allowed energy to settle into more stable forms, and the first building blocks of matter began to appear. Quarks combined to form protons and neutrons. These particles became the foundation for atomic nuclei. At this stage, however, the universe was still far too hot for full atoms to exist. Instead, it was filled with a dense, glowing plasma composed of charged particles moving at high speeds. This plasma was not transparent. Light existed, but it was constantly scattered by interactions with electrons and other charged particles. Photons could not travel freely, and the universe remained opaque. Within the first few minutes, an important process took place. Protons and neutrons began to combine, forming the nuclei of the simplest elements. Hydrogen nuclei formed first, followed by helium and small amounts of lithium. This process is known as primordial nucleosynthesis. It determined the initial chemical composition of the universe, setting the stage for everything that would come later. The proportions of these elements were not random. They depended on the conditions of the early universe, including its temperature, density, and rate of expansion. By studying the abundance of these elements today, scientists can test their models of the early universe. Research conducted by organizations such as ESA and missions supported by NASA continue to refine our understanding of these processes. At this stage, the universe was still relatively simple. It contained mostly hydrogen and helium with very little variation. There were no stars, no galaxies, and no complex chemistry. Yet within this simplicity lay the foundation for all future structure. Small fluctuations in density were already present. These tiny differences, almost insignificant at first, would later grow under the influence of gravity. Over time, they would lead to the formation of the first large-scale structures. It is remarkable to consider how much emerged from these early conditions. From a nearly uniform plasma, the universe would eventually develop into a vast and intricate system filled with galaxies, stars, and planets. Even now, scientists continue to study these early moments, using both observation and simulation. Advances in technology, including launch systems developed by companies like SpaceX, make it possible to send more advanced instruments into space, improving our ability to gather data. The formation of matter was not a sudden event, but a gradual transition. It was a process shaped by expansion, cooling, and the interaction of fundamental forces. And within that process, the universe began its long journey from simplicity toward complexity. For a long time after the formation of the first atomic nuclei, the universe remained quiet, dark, and slowly expanding. There were no stars yet, no galaxies, and no visible sources of light as we understand them today. Space was filled mostly with hydrogen and helium gas, gently moving under the influence of gravity. This period is often described as the cosmic dark ages. It was not dark in an absolute sense, but there were no luminous objects to illuminate space. The universe existed in a kind of calm stillness, with matter distributed almost evenly, yet not perfectly uniform. Within this nearly uniform distribution, very small fluctuations in density began to grow. Regions that contained slightly more matter exerted a slightly stronger gravitational pull. Over time, this caused nearby gas to drift inward, slowly increasing the density of these regions. This process was gradual. It took millions of years for these small differences to become significant. But gravity is patient. Given enough time, it can turn the smallest imbalance into a major structure. As gas accumulated in these denser regions, it began to collapse under its own gravity. The collapsing material heated up as it was compressed. Eventually, temperatures and pressures at the core of these regions became high enough to trigger nuclear fusion. This moment marked the birth of the first stars. These early stars were very different from the stars we see today, because they formed from almost pure hydrogen and helium. They lacked heavier elements that influenced star formation in later generations. As a result, many of the first stars were likely much larger and more massive than typical stars today. Massive stars burn their fuel quickly. They shine intensely but do not live long. The first generation of stars, often referred to as population 3 stars, may have lived only a few million years before reaching the end of their life cycles. Despite their short lifetimes, their impact was enormous. Inside their cores, nuclear fusion created heavier elements. Hydrogen fused into helium, helium into carbon, and so on, building the first complex elements in the universe. These elements did not exist before the first stars formed. When these massive stars reached the end of their lives, many of them exploded as supernovae. These explosions were powerful enough to scatter newly formed elements into the surrounding space. This process enriched the universe. Regions that once contained only simple elements now contained the building blocks for more complex chemistry. Future generations of stars would form from this enriched material. These stars would be different, often smaller and more stable, with longer lifetimes. Over time, the universe became more chemically diverse. Scientists today cannot observe the very first stars directly. They are too distant and too faint to detect with current instruments. However, their existence is inferred from the chemical composition of later stars and galaxies. Observations made using advanced telescopes, including the James Webb Space Telescope, allow scientists to study ancient galaxies and gather indirect evidence about these early stars. Research supported by NASA continues to explore this early period, combining observational data with theoretical models. The first stars represent a turning point in cosmic history. They transformed a simple universe into one capable of complexity. Without them, there would be no heavy elements, no planets, and no life. They were brief, intense, and transformative. The formation of the first stars brought light back into the universe, but this light did more than simply illuminate space. It began to change the state of the universe itself. Before the first stars, most of the hydrogen in the universe existed in a neutral state. This neutral hydrogen absorbed and scattered light in a way that prevented it from traveling freely across long distances. When the first stars ignited, they emitted large amounts of high-energy radiation. This radiation interacted with the surrounding hydrogen gas, gradually ionizing it. Ionization means that electrons were stripped away from atoms, turning neutral hydrogen into charged particles once again. This process changed how light interacted with matter. As more stars formed and more radiation filled the universe, larger regions became ionized. Over time, those ionized regions expanded and began to merge. This era is known as reionization. It marked the end of the cosmic dark ages and the beginning of a more transparent universe. Light could now travel much greater distances without being scattered or absorbed. Reionization did not happen instantly. It was a gradual process that took hundreds of millions of years. During this time, the universe transitioned from a mostly neutral state to a mostly ionized one. Understanding this transition is one of the key goals of modern cosmology. Observations from missions supported by NASA and data from telescopes like James Webb Space Telescope help scientists study this period in greater detail. By analyzing light from distant galaxies, researchers can estimate when reionization occurred and how quickly it progressed. This phase is important because it set the conditions for everything that followed. Once the universe became transparent, light from stars and galaxies could travel freely, making it possible for structures to be observed across vast distances. It also allowed galaxies to interact with their surroundings in new ways, influencing future star formation and cosmic evolution. At the same time, reionization reflects the growing complexity of the universe. It shows how the formation of stars can influence not only local environments, but also the state of the universe on a much larger scale. Private space companies like SpaceX play an indirect role in this ongoing research by enabling the launch of advanced observational instruments, expanding humanity's ability to study distant cosmic history. The end of the Dark Ages was not a dramatic event in the way we might imagine. It was a slow, steady transformation driven by the light of the first stars. And in that transformation, the universe became a place where structure, light, and complexity could continue to grow. As the first generations of stars lived and died, the universe continued to evolve. What began as isolated regions of collapsing gas slowly developed into larger and more complex systems. Gravity, working steadily over immense spans of time, began to organize matter into structures that would eventually become galaxies. These early galaxies did not appear suddenly. They formed through a gradual process of accumulation and merging. Small clusters of stars and gas clouds came together, influenced by gravitational attraction, forming larger and denser systems. In the beginning, these galaxies were not the well-defined spiral shapes we often imagine today. Instead, they were irregular, compact, and highly dynamic. Their internal structure was constantly changing as new stars formed and older stars ended their lives. Collisions between proto-galaxies were common. When two early galaxies encountered each other, they did not simply pass by. Their gravitational fields interacted, pulling stars, gas, and dust into new configurations. Over time, these interactions helped shape the larger galaxies we observe today. Inside these early galaxies, star formation occurred at a much higher rate than in most galaxies now. Gas clouds were abundant, and conditions favored rapid collapse and ignition of new stars. This meant that early galaxies were often bright, energetic environments filled with intense radiation and frequent supernova explosions. These explosions played an important role in distributing heavy elements throughout the galaxy. With each generation of stars, the chemical complexity of the universe increased. Elements like carbon, oxygen, and iron became more common, making it possible for more complex structures to form later. Observing these early galaxies is one of the main goals of modern astronomy. Because they are so distant, the light we see from them today has traveled for billions of years. The James Webb Space Telescope has been particularly important in this area. Its ability to detect infrared light allows it to observe galaxies that formed very early in the history of the universe. Data collected by NASA and international collaborations suggest that some galaxies formed earlier than expected. In some cases, they appear more massive and more developed than current models predicted. This has led scientists to reconsider how quickly galaxies can form and evolve. It raises questions about whether our understanding of early cosmic conditions is complete. Despite these uncertainties, one thing is clear. The formation of galaxies marked a major step in the development of the universe. It was the stage where matter began to organize into large-scale structures, creating the framework for everything that would come later. Galaxies are not just collections of stars. They are dynamic systems shaped by gravity, time, and the continuous cycle of star formation and destruction. And even now, billions of years later, they continue to evolve. Long before galaxies, stars, or even atoms existed, the universe may have experienced a phase of expansion unlike anything that followed. This phase is known as cosmic inflation. According to this idea, the universe expanded extremely rapidly in a very short period of time, far faster than the rate of expansion we observe today. During inflation, space itself stretched dramatically. Distances between points increased at an exponential rate, smoothing out irregularities and shaping the large-scale structure of the universe. This process helps explain why the universe appears so uniform when observed on large scales. Regions that are now very far apart were once much closer together, allowing them to share similar conditions before being rapidly separated. Inflation also provides an explanation for the origin of small fluctuations in density. In the earliest moments, tiny variations in energy existed at quantum scales. Inflation stretched these variations to cosmic sizes, turning them into the seeds of future structure. These fluctuations would later grow under the influence of gravity, eventually leading to the formation of galaxies and clusters. Evidence for inflation comes from observations of the cosmic microwave background. This faint radiation carries patterns that match predictions made by inflationary models. Missions supported by NASA have mapped these patterns with increasing precision, allowing scientists to test different versions of the theory. Even so, inflation is not fully understood. Researchers are still exploring what caused it, how long it lasted, and what physical mechanisms were involved. Some theories suggest that inflation may be connected to deeper properties of space and time. Others propose that it could be part of a larger framework involving multiple universes. These ideas remain speculative, but they highlight how much there is still to learn about the earliest moments of existence. Inflation is important, not only because of what it explains, but also because of what it suggests. It shows that the universe we observe today may have been shaped by processes that operated under conditions very different from anything we experience now. It also reminds us that even the largest structures in the universe may have originated from the smallest fluctuations. Private space companies, such as SpaceX and Blue Origin, are helping to expand access to space, making it possible to launch more advanced instruments and gather more precise data. These efforts support the ongoing search for answers, allowing scientists to refine their understanding of cosmic inflation and its role in the evolution of the universe. As galaxies continued to form and evolve, scientists began to notice something unusual. The visible matter in the universe, the stars, gas, and dust that we can observe, did not seem to account for all of the gravitational effects that were being measured. Galaxies rotated in a way that suggested there was far more mass present than could be seen. Stars at the outer edges moved faster than expected, as if they were being held in place by an invisible force. This led to the concept of dark matter. Dark matter does not emit light, does not absorb it, and does not interact with electromagnetic radiation in any direct way. It cannot be observed through traditional telescopes. And yet, its presence can be inferred through its gravitational influence. In the early universe, dark matter likely played a fundamental role in shaping structure. While ordinary matter was still interacting with radiation and moving relatively freely, dark matter began to form gravitational wells. These invisible structures acted as a kind of scaffold. Gas and visible matter gradually fell into these regions, guided by gravity. Over time, this process helped form the first stars and galaxies. Without dark matter, the formation of structure would have been much slower and less efficient. The universe might have remained far more uniform, lacking the rich complexity we observe today. Even though dark matter cannot be seen directly, its effects are visible everywhere. Galaxies cluster together in patterns that reflect the distribution of dark matter. Large-scale cosmic structures, sometimes described as a cosmic web, are shaped by its presence. Scientists continue to search for direct evidence of dark matter particles. Experiments are conducted deep underground, in space, and in particle accelerators. Research supported by NASA and the international collaborations aims to better understand this mysterious component of the universe. At the same time, companies like SpaceX contribute by launching instruments that allow more precise observation of cosmic structures. Despite all of this effort, the true nature of dark matter remains unknown. It is one of the most significant unanswered questions in modern science. And yet, even without fully understanding it, we can see that it plays a crucial role in shaping the universe. It is the invisible architecture behind everything we observe. For hundreds of thousands of years after the Big Bang, The universe remained filled with a dense, glowing plasma. Light existed, but it could not travel freely. Photons were constantly scattered by interactions with charged particles, preventing them from moving across long distances. This changed during a period known as recombination. As the universe expanded and cooled, electrons combined with protons to form neutral atoms. This reduced the number of charged particles, allowing light to travel freely for the first time. This moment marked the release of the first light that could move across the universe without constant interference. That light still exists today. It is known as the cosmic microwave background, a faint radiation that fills all of space. It is not visible to the human eye, but it can be detected with specialized instruments. It provides a snapshot of the universe at a very early stage, when it was only a few 100,000 years old. Tiny variations in this background radiation reveal differences in density that would later grow into galaxies and large-scale structures. Missions supported by NASA have mapped this radiation in extraordinary detail, allowing scientists to study the early universe with remarkable precision. These measurements have become one of the most important sources of information about the origins of the universe. The cosmic microwave background is, in a sense, a memory. It is the oldest light we can observe, carrying information from a time when the universe was still very young. And even now, billions of years later, it continues to travel through space, quietly reaching us from every direction. Observing the early universe is not simple. The farther away an object is, the longer its light has taken to reach us. This means that the earliest galaxies are also the most distant and faint. For a long time, this limited our ability to study them. The launch of the James Webb Space Telescope changed that. This telescope is designed to observe infrared light, which allows it to detect objects whose light has been stretched by the expansion of the universe. Using Webb, scientists have been able to observe galaxies that formed very early in cosmic history. Some of these galaxies appear to be more massive and more developed than expected. This challenges existing models and raises new questions about how quickly structure can form. Organizations like NASA continue to analyze this data, working with researchers around the world. At the same time, the broader space industry continues to evolve. Companies such as Blue Origin and SpaceX are helping to make space more accessible, enabling future missions and new discoveries. The study of the early universe is not just about looking back in time. It is also about building better tools, refining models, and expanding our understanding of reality. Each new observation adds another piece to the puzzle, and often it also reveals how much we still do not know. It is easy to think of the early universe as something distant and abstract, but in reality, it is directly connected to everything that exists today. Every atom in your body was shaped by processes that began in those early moments. The hydrogen formed shortly after the Big Bang, the heavier elements created in stars, and the structures formed by gravity all contribute to the existence of planets, life, and consciousness. Understanding the early universe is a way of understanding origins. It also allows scientists to test the laws of physics under extreme conditions. The early universe cannot be recreated in a laboratory. It represents a natural environment where the fundamental forces of nature operated at their limits. By studying it, researchers can gain insights into how these forces behave and how they may be connected. There is also a broader perspective. When we consider the vast timeline of the universe, human history becomes a very small part of a much larger story. This does not make it less meaningful. Instead, it places it within a wider context. Space agencies such as NASA and ongoing advancements in private spaceflight continue to support this exploration. The more we learn, the more we understand how interconnected everything is. The early universe is not just a distant past. It is the beginning of a continuous process that leads all the way to the present moment. Despite everything that has been discovered, much of the early universe remains a mystery. We do not fully understand what caused the Big Bang. We do not know the true nature of dark matter. We are still trying to explain dark energy, the force that appears to be accelerating the expansion of the universe. There are also deeper questions. Was the Big Bang the true beginning or part of something larger? Does the universe have boundaries, or is it infinite? Are there other universes beyond our own? These questions are not easy to answer. They may require new physics, new theories, and new ways of thinking. But this uncertainty is not a weakness. It is part of what drives scientific discovery. Science moves forward not by knowing everything, but by exploring what is not yet understood. The early universe remains one of the most profound frontiers of knowledge. It is both a beginning and an ongoing mystery. And as the universe continues to expand, the light from its earliest moments continues to travel outward, carrying with it the story of everything that has ever existed, quietly, steadily, and endlessly.